In this video and in the next couple of videos, we're going to take a look at some theorems related to derivatives. We will start with a theorem that we are pretty familiar with. That is, if f is differentiable on an open interval from a to b, and if that function assumes its maximum or its minimum at a point c in that open interval, then the derivative of the function at that point c has to be equal to 0. So let's take some time and prove this theorem. So let's start with, suppose f assumes its maximum at c. In the open interval a to b. What does it mean if it assumes its maximum? Well, then that means that f of x is less than or equal to f of c for all x in the open interval from a to b. Right? So f of c is the largest value, function value. So we can let x sub n be a sequence. So let this be a sequence that converges to C. Such that A is less than x sub n is less than C. Right, so we have these values that are to the left of C that are converging to C. So values between A and C that are converging to C. And we want that to be true for all n. Since, what do we know about f? Well, we know f is differentiable at c. Since f is differentiable at c, then we know that the sequence that consists of those function values at x sub n minus f of c over x sub n minus c, that sequence has to converge. It converges to f prime at c. But what do we know about this sequence right here? Well, the way that this sequence has been chosen, we can note that every term in the sequence every single term in this sequence is non-negative. How do we know that? Well, we know that because f of c is that maximum value, and so up here on top we're going to have a value that is no larger than f of c, so that's either going to be 0 or it will be positive. 0 or negative there on top, and we also know that x minus c is going to be negative, so we'll have either 0 or a negative divided by a negative, and so it's going to be either 0 or positive. Yeah. So I'll write that down. So since f of x sub n is less than or equal to f of c, and x sub n is less than c. So then what does that tell us about f prime at c? Well, we now know f prime at c is greater than or equal to 0. So now we'll go through a similar argument with a second sequence. Let's call it y sub n. Such that So this time we are going to choose that value, the sequence, to be values coming from the right of C. So that for all n. So again, since f is differentiable at C, the sequence f of y sub n minus f of C over y sub n minus C converges to f prime of C. Note that every term here is non-positive. All right, so up here on top, we will still either have 0 or a negative. Here on bottom, we will have a positive. So if it's 0 on top, we get 0. And if it's negative on top divided by a positive, we would get a negative. And so we get f prime of C is less than or equal to 0. Since we have 0 is less than f prime of C is less than 0, less than or equal to 0, then f prime of C has to be equal to 0. So that addressed what happens if f assumes a maximum at C. So to prove this, if f has a minimum at C, then we can use the same argument but with negative f. Perfect. All right, we will see you in our next video.